Thank you for having me today at this conference. It's an honor to be able to present our paper, How Many Features is an Image Worth? Multi-channel CNN for Steering Angle Prediction in Autonomous Vehicles. So first, here's a brief overview of my presentation. I'll begin with providing the motivation for this work, followed by some more pointed research questions this paper sought to answer. And then next, the proposed solution is presented, followed by the results of the experiments. And finally, I'll just wrap up with some concluding remarks. Okay, so the motivation for this work is as follows. Various CNN models have enabled the prediction of steering angles using road images taken from onboard cameras. For example, back in 1989, CMU's Alvin test vehicle showed it could follow the road based on outputs from a shallow 3-layer network. And then in 2016, the NVIDIA Corporation created a convolutional neural network architecture called PilotNet, which featured a full end-to-end steering angle prediction network that used only image pixels as input and no other human design features to train it. But given this immense progress, issues of model robustness to a variety of environments and driving conditions still prevent optimal steering performance. Attempts have been made to increase the accuracy and robustness via sensor fusion that's incorporating things such as radar and LiDAR. However, debate has recently arisen between automotive companies as to which method is best suited for full self-driving vehicles. And this is mainly a debate between companies like Tesla, who believe full self-driving can be accomplished with cameras only, and most other companies taking the sensor fusion position. With this, the main objective of this work is to put the image-only paradigm to the test and learn whether 2D RGB monocular camera images alone can be strengthened to provide sufficient signaling power to perceive the driving environment and provide accurate end-to-end steering angle predictions. Now that we have a motivation for pursuing this research, we can look at some of the more direct research questions this paper seeks to answer. First, can image segmentation and depth estimates provide enhanced signaling features to improve the accuracy and robustness of steering angle predictions? The idea here is to understand whether we can extend the spatial perception of the original image with useful information similar to how humans navigate. Segmentation allows the model to detect the presence of particular objects, but can also provide an accurate mapping of the location and the boundaries of these objects in an image. For example, in this case, you can distinguish the road from other objects in the image. Depth estimations provide an additional spatial dimension to perceive the environment at various distances during navigation, which is critical for things like obstacle and collision avoidance, but also for determining how the path ahead is changing. For example, we have the ability to perceive if the road in front of us begins to change elevation or curve sharply by perceiving how quickly distances between one point to another are changing. Next, can these estimates be generated from RGB images alone to provide sufficiently significant signaling power to an end-to-end steering angle prediction network? So RGB images can provide the primary environmental context relatively cheaply through onboard cameras. And if we can minimize the raw data input to these, we can also reduce the amount of hardware cost and computation necessary while still achieving optimal performance. Next, is it possible to extract and synthesize the outputs of independently developed pre-trained models to use as inputs to another network? This is similar to an idea of transfer learning. However, in this instance, we are transferring the outputs of models designed for a particular task for use in a larger network. The goal here would be to allow for modular network designs that can be worked on by different groups without needing to know the full context for how the model will be used. Each network can be continually trained, updated, and optimized to provide better inputs into the larger network. And stacking different networks together can expand the functionality, particularly in end-to-end networks that would be desired in autonomous vehicles. And finally, the last two questions can go together. When combining all of these additional inputs, What must the overall network be to provide the best performance? And what impact do each of these additional features have on the overall steering predictions? It isn't guaranteed that these additional signals will improve performance, and by analyzing each of their contributions, we can understand what features are important. Oops. So here we have the proposed solution to address these questions. What can be seen here is the proposed network topology of this end-to-end steering angle prediction network. We can see that it starts with RGB images taken from an onboard AV camera. The images are then sent to a road segmentation network and a depth map network. The segmentation network was pre-trained using a standard UNet architecture common to many segmentation networks, and the depth model was pre-trained on an unsupervised CNN network that was able to learn depth estimates from sequences of unlabeled video frames. The model allowed for single frame depth estimates at inference time, which is what's being leveraged here. The RGB image data, segmentation outputs, and the depth estimates are input into individual CNN channels to extract the relevant features from each of these different representations. The outputs of each CNN channel are then concatenated together before being passed into a fully connected network, with the output being the steering angle prediction for the given scene image. On the right, you can see the three different image representations and the purpose they serve. The top is the raw image, the middle is the road segmentation output, and the bottom is an image representation of what the depth estimates would look like. As you can see, the full multi-channel CNN network is being provided the full environmental context, the location of the road in the image, and a third spatial dimension of the objects in the environment. All this serves to provide the model with sufficient signaling power to learn the steering angle in each frame. So to build this multi-channel network, we first focused on building individual CNN networks that optimize the performance of each of these image representations. It was thought that by doing it this way, the most relevant features of each could be extracted for use in the full network and providing the best steering angle predictions. The first network made was the CNN for the RGB inputs. Because NVIDIA showed how powerful their end-to-end network was originally for steering angle predictions, PilotNet was used as the inspiration for this network. The network consists of 5 convolutional layers, followed by a fully connected network. Because the image dataset was slightly different than what PilotNet had originally had in terms of resolution, the model architecture needed to be slightly modified. And you can see the comparison of the RGB model that we made compared to NVIDIA's PilotNet on the left. Next, the segmentation and depth CNNs were built. Initially, it was thought to follow the same architecture theme as the RGB model. However, it's found that a more VGG-style architecture network worked best for these representations. Each model had 2 VGG blocks consisting of 2 convolutional layers, followed by a max pooling layer. A fully connected network was added after the feature extraction layers to provide a steering angle prediction. You can see the segmentation input network in green and the depth input network in red on the right. It should be noted that while the RGB input consisted of a 3-channel input, the segmentation and depth networks only contained a single channel input. After each individual network is built, they were combined into the full multi-channel CNN network seen on the left. To do this, the fully connected layers were removed from each individual channel and then flattened the outputs, and each were all combined. Now, all the extracted features from each representation are passed to a new fully connected network, with the end result being a steering angle prediction for a given frame at the output. Now, in order to assess the effects of the representations on the steering angle prediction, another set of multi-channel CNN networks were created with all possible combinations of image representations, which can be seen on the right. The same procedure to construct the full model was followed here by removing the individual fully connected layers and then concatenating those features and passing them into a fully connected network. So each model underwent a training procedure at the individual level and at the combined network level. The dataset used was the Udacity self-driving competition dataset consisting of over 33,000 RGB images taken from an onboard camera and were divided into an 80-20 training and test split. So this dataset is readily available and has been used on many other steering angle prediction networks, which provides a good benchmark to compare results against. All the images were prepped for the pre-trained models to conform to their required inputs and off-the-shelf networks. This included resizing, cropping, and downsampling as necessary. The pre-trained models produced their own individual results, and then all the image representation inputs were normalized prior to being used in the CNN networks. The Keras API with Tensor GPU supported backend served as the deep learning framework for these experiments. The loss function used for optimization was mean squared error, which penalizes larger errors more severely, which is desirable in an application like this, where low steering angles are paramount. The models were evaluated using the root mean squared error and mean absolute errors. Using the MAE together with RMSE, the model performance can be better understood. The magnitude of the differences between the two informs how high or low the variance is in a set of predictions, with higher magnitudes indicating more variance of the errors and lower magnitudes indicating less. The Atom optimizer was used, and the number of epochs of training varied between 20 and 50, depending on which model it was, and the ideal batch size was found to be 50 samples. A checkpoint was implemented to ensure the best model and weights were saved for later use, and also saved it before the model began to overtrain and overfit, I should say. And finally, the weights of the individual networks were left unfrozen when combined into the multi-channel network. So while the individual network weights were found already when trained individually, it was thought to let the network optimize the weights again for the given network when other features are being used for steering angle predictions while keeping the individual model architectures the same. Finally, we arrive at the results of the end-to-end steering angle prediction networks. In table 1, you can see the mean absolute error and root mean square error for each network architecture from individual networks up to the full multi-channel networks and its variants. As you can see, the full multi-channel CNN network did not have the best performance overall, as expected. The RGB plus depth network provided the lowest steering angle prediction errors when tested on the Udacity dataset. It can be seen the segmentation only model performed the worst overall. However, it can also be seen that any network that combined the RGB model with another feature representation provides overall better performance than any of the individual models. When the segmentation model and depth models are paired, this produced the worst performing multi-channel CNN, which makes sense given both models underwhelmed individually and lacking the RGB inputs. The combination of the two poor performing models yields a slightly better, but still overall poorer performing model. To better illustrate the model performance, the single models and combined models are compared to the ground truth over a subset of test samples in the top figures on the right. Significant performance can be seen between the single and multi-channel models, reinforcing the idea that different image inputs are useful for the steering prediction task. The contrast between the best and the worst model is stark. The bottom left figure shows the best performing model, while the worst performing model can be seen on the right. The best model is able to tightly follow the ground truth data over a wide variety of angles, ranging from -50 to +70 degrees, while the worst is unable to reliably follow the trajectory at all. The reason this may be the case will be explained on the next slide. Finally, the performance of the best models compared to past performances of models using other methods in table 2. It can be seen that the RGB and depth model outperform them all, including the original NVIDIA PilotNet architecture, as well as others that incorporate sequential data with LSTMs or 3D CNNs, or using transfer learning from common CNN backbone architectures. And it should be noted that every one of these examples in this table were all evaluated on the same Udacity data set. Another way to analyze the results of the networks is to look at the correlation between the ground truth and the predicted steering angles, as well as the ground truth and the angle prediction errors. Each set of plots illustrates the trends of the real and predicted angles. A perfectly performing model would have a 1-to-1 correlation with a slope of 1 with the predicted angle matching exactly with the ground truth. And the error plots to the right would have a 0 sloping trend line with 0 error between the prediction and the ground truth. It can be seen that the better models contain less dispersion between the real and predicted angles, with the data points tightly clustered around the trend line, while the worst models have the opposite behavior. The best performing model, the RGB plus depth model, illustrates this with a trend line with slope close to 1 and a shallow trend line on the error with densely populated plots around these lines. The segmentation model in the middle shows a complete performance breakdown where the data is wildly dispersed and trend lines have unfavorable slopes. It can be seen there are many similar steering angle predictions in the segmentation model over the entire range of the possible values. This was suspect, and the reasoning this occurred was hypothesized to be due to the off-the-shelf model not performing well on the Udacity dataset. The original model was trained on the Kitty dataset, which is common for segmentation training. So the model may be struggling to make inferences more generally. This means that even though the segmentation model performed very poorly here, the use of segmentation for enhanced features for steering predictions is still open to further study with a better performing segmentation model. It should be noted as well that all models struggle somewhat with larger steering angles. This is likely due to the simple fact that the data set did not have an equal representation of larger steering angles compared to the small angles. Most often during driving, the roads are relatively straight, so obtaining larger angles with sharp turns is much more difficult. One way to address this would be by either increasing the overall samples with additional larger turning angles, or you can perform an upsampling of the given large angles already in the data set to help the model learn better. With all this analysis provided, we can now see how the models perform on the real images themselves. A portion of the data set was used to make predictions over the Udacity data set and compared to real-time performances to each other. So here we can see how the end-to-end network performs in real time. Using the RGB model as the baseline, since it's the simplest and original setup, the other trained networks can be seen in action. The green dot on the blue circle represents the ground truth angle for a given frame, where the red indicates the predicted angle. It's easy to see the difference between the best and worst performing model. The segmentation model is very unstable and often predicts inaccurate steering angles, while the RGB plus depth model is very stable and accurately predicts angles even over larger angles. It still makes some mistakes, but the accuracy and robustness stands out from the rest. So I'm just going to let this play for a little bit just to kind of give you a little bit more time to kind of see how these different models are performing. You can see the predictions kind of bouncing around on the depth and segmentation models up top, while the full model and the other RGB plus segmentation model, they're actually pretty stable. Looking back at the table, they had very close MAE and RMSE evaluation errors, but when the calculation was done, it was still found that the RGB plus depth model provided the best results. So it might be hard to decipher the differences between the full model, which we assume to be the best model. But in this case, we had to take out the segmentation inputs to achieve the overall best performance. All right, so in conclusion, we have demonstrated the effectiveness of multi-channel CNNs to improve performance of steering angle predictions without the introduction of raw feature signals other than the images provided from onboard camera of autonomous vehicles. Depth data computed from a pre-trained model in combination with an RGB image provided the best overall steering angle predictions. Networks involving road segmentation provided the worst performance, likely due to the pre-trained model's inability to make predictions on a different data set than the one it was trained on, or the data required an alternate pre-processing procedure to predict effectively. The best multi-channel CNN exceeded performance of previous models using various network architectures that include spatial and temporal elements, leveraged transfer learning techniques, or implemented parallel auxiliary networks to feed various levels of features to layers of a single CNN network. Additional work can further enhance the steering angle prediction network through the use of better performing segmentation and depth models, increasing the sample size, including more large angle samples and a more diverse set of driving conditions, or include temporal aspects, which still satisfies the objective of using only image data as inputs. So with that, that's all I have, and I'll be happy to take your questions.